Hi, folks. So far in this little series of lectures, we've been talking a lot about supply and demand curves and how we use them to better understand some of the sustainability problems that come with incomplete markets. But when we start talking about things like open access resources and public goods, although the supply and demand framework is very interesting and illustrative, there are additional lenses that we can apply from mathematics to give us different perspectives on these systems. And in this short discussion, I'm going to introduce some game theoretic perspectives to handle these types of problems. So let's get to that. Let me share a screen here. All right. So this is not going to be a comprehensive introduction to game theory by any means, but this is just a brief introduction to a small subset of game theory that allows us to get at these two problems of open access resources and public goods. So what is, so the area of game theory that we are focusing on here is going to model the decisions made by individuals who choose among discrete alternatives. So what do I mean by that? Well, if you watched my open access resource video, then that one ended up coming down to, in order to really understand the open access problem and what was going on, it really came down to understanding how people make decisions about when to enter or not enter a resource, to decide to exploit or not exploit. It was less about the question of how much does an individual exploit. It was really the question of, does an individual decide to exploit? And when you then put a lot of those individuals together, then you get an emergent phenomenon that ends up being the kind of the negative outcome that you get with a lot of open access resources and problems. And so we are going to focus here on a two-player problem. So what happens when two individuals are trying to make decisions where their outcomes are coupled? And so the decisions of those two individuals end up together jointly determining the reward that each individual receives. Now, most people are familiar when the first time they ever hear about game theory, they're probably introduced to something called the prisoner's dilemma. Now, I'm not going to use the prisoner's dilemma as a model for either of these two open access resources or public goods. I think there are other games that better capture that, but I am just going to give a brief review of that just because it's something that I think a lot of people have already seen, or at least it's a good entry point into this kind of game theory. So let's consider two players that each can make a decision, and that decision is to so-called cooperate or defect. And the setting here is two individuals are, say, picked up by some police, and the police don't have enough information to pin a crime on either one of them, but they know that these two individuals do themselves have enough information that they can give that would allow the police to pin the crime in its completeness on one of them. And so all the police need is for one of them to rat out the other one, to give out information on the other one. So long as both of them do not give any information, then the two end up getting off with only spending a very small amount of time in jail. But if one of them ends up giving information on the other one and the other one does not, then the one who ends up ratting them out gets off free, and the one who ends up who ends up not giving out information goes to jail for the whole time. If they both end up giving information on each other, then the police can end up, and this is where it gets a little bit hairy, but in this particular case, then they go away for a longer time than they would if they were to cooperate, but it's not necessarily as bad as if one of them ended up ratting out the other one. So the metaphor breaks down a little bit, but still, it's just generally what is referred to as the prisoner's dilemma, and we represent it with a so-called payoff matrix. And in that payoff matrix, we are going to have, it's basically going to be a little grid here. So I'll make enough room for a 2x2 space here. Maybe I'll do it right here. It'll be a little small, but I think we can make this work. Maybe I'll make that a little bit wider. Okay. And so this grid here, which I'll then subdivide, you can view, we'll say on the side here, on the left side here, we will have player 1 decisions. And in the way I write the reward, which we'll see in a second, you'll also see the player 1's reward will show up over there too. So the player 1 can decide to defect, or player 1 can decide to cooperate. And if player 1, and then I guess maybe I'll just jump to player 2 and then we'll talk about the outcomes. So then player 2 decisions, or player 2 decisions. So maybe player 1 decisions, I'll draw a little line. And so player 1 can either decide to do either one of these things, and then player 2 can also decide to cooperate or defect. And so if under the case where player 2 cooperates and player 1 cooperates, then and by cooperating, then that means that they neither of them talk. And so they're both cooperating with each other. And so under those cases, we're going to say that, well, they both have to spend a night in jail or something, but they get off the next day because they don't have enough information to hold them. So in that case, player 1 gets -1, and player 2 also gets -1. And I am going to just symbolically refer to this -1 as a quantity R, uppercase R. And this is a reward for cooperation. So I'll also just write that down here just so we remember it, is that R and R. And so this is just the symbolic version of this if we didn't have any numbers. All right, and then we say, all right, so what are the other outcomes here? Well, if player 1 cooperates, but player 2 defects, so player 2 gives information on player 1, then player 1 is going to be in for the whole time. So player 1 is going to be, they are going to be out and in jail for, whatever 5 units is, so it's bad. All week, a year, I don't know, it's bad. But player 2 gets to leave immediately. They're done. They got their deal. So they have 0. So 0 is actually a good outcome here. And so I am going to refer to the -5 here as the sucker's penalty, S. So I'll write that here as S. And and then player 2, they are going to, that 0 is going to be the temptation to defect, T. And then the symmetric case on the other side. And so if instead player 2 decided to cooperate, but player 1 ratted player 2 out, then we end up getting the same outcome. It's just flipped, who ends up getting the different rewards. So in that case, we're going to have that player 1 is going to get our temptation to defect, and player 2 is going to get the sucker's penalty S. Oh, the sucker's penalty -5. And then I can get my colors correct here, -5. And then I'll again write that as here we have S and T, just with the colors flipped. And then finally, if they both decide to defect, which means they both tell on each other, then in that case, we have a punishment for them both defecting. And so in this particular case, you can imagine that, well, if one guy ratted out the other one ratted out that one, then the police have enough information, but now that they're conflicting stories, then maybe it's not quite as strong of a case. And so they end up being able to put the 2 of them away for 2 years instead of 1 of them away for 5 years. And so, so that's, that's maybe the story that we tell here. So this is going to be a -2 for both players. And I'm going to refer to the -2 as a penalty for mutual defection, or punishment maybe for mutual defection. So I'll write that as a P on both colors here. And so there you have it. That is the prisoner's dilemma. Now, and I guess I should write that in the prisoner's dilemma, then you notice that there is a relationship between the quantities. In order for a prisoner's dilemma to be a prisoner's dilemma, you have to have a payoff matrix with these 4 things, T, R, P, and S, and they have to be ordered in that direction. And so, in other words, in order for this to be a prisoner's dilemma, then, so if I were to write this is a prisoner's dilemma, if you've got that the temptation to defect is greater than the reward for cooperation, which is going to be greater than the punishment for mutual defection, which will then be greater than the sucker's penalty, S. And so that ordering right there is really what makes this a prisoner's dilemma. If you ended up reversing some of those, it might be another interesting game, but it wouldn't be a prisoner's dilemma. Now, what's special about the prisoner's dilemma is the fact that the outcome that is up here, the cooperate outcome, this one is the socially efficient outcome, the socially efficient allocation of punishment. You can view it that way. So I'll also call this, I'll say it's socially efficient. To cooperate, both of them cooperate. And you can check that this actually is, at least the way I've written it, Kaldor-Hicks efficient. In other words, it is true that, let's say you can actually, player 2 here can go from -1 to 0 and pick up a point. But in order for player 2 to increase by 1 point, then it causes player 2 to decrease by 4 points. And so because player 2 couldn't possibly compensate player 1 for that, then that is not a Kaldor-Hicks improvement. So if you do that game throughout all of here, even here, if you do that whole game here, then what you find is that this corner up here is going to be Kaldor-Hicks efficient. That is the spot where you want to be in the socially efficient case. This is, you want everybody to cooperate. This is the best thing for you to do. But in the prisoner's dilemma, it turns out that you're going to find that most individuals are attracted to the exact opposite diagonal square, which is down here. And that is because this is a so-called Nash equilibrium. Which is a totally different concept. And this is sort of captures what we mean to be sort of selfishly optimal, or you might say pragmatic. So I'd say make pragmatic with no coordination. So if you have no idea what someone else is going to do, you got to look out for yourself, and you got to ask yourself, what's the best thing I can do given that everyone else can't count on me as well? And so what you end up with is a Nash equilibrium is something where there is no way to unilaterally improve. For anyone. So, and what we mean by unilaterally improve is that if you found yourself in that position, so I defected and my neighbor defected, if we are both in that, that all defect situation, then any change that I make is not going to be good for me unless my neighbor also makes a change. So if my neighbor stays at defect, then my change to cooperation is only going to be worse for me. And so that's what we see here, is that you can see that if player 2 is already getting a -2 for defecting, if player 2 then shifts to cooperation, player 2's -2 is going to go down to -5. Well, that's not good. And it's the same with player 1. If player 1's already getting a -2 for defecting, if they know that player 1 isn't going to change, then player 1, if they shift to cooperation, then player 1 is also going to go down to a -5. And so in both of their cases, if they cannot coordinate, then this is the best thing they can do. It's Nash optimal. And so that ends up being this all defect solution, even though it is socially inefficient, ends up being the solution that most players will end up choosing, unless you have some other way to create coordination or coupling between them. And there's a lot of really cool research handling the prisoner's dilemma and how you solve it. So another way to view the Nash equilibrium is kind of a no regret condition, is that if the system, if you find yourself cooperating, then there's only one way that cooperation really works out for you, and the other way you're really going to regret cooperating. If you find yourself defecting and you notice the other guy cooperated, then you might think, gee, man, if we both had cooperated, then that might have turned out better, but I'm pretty happy the way things turned out as it was. And so there's really no, you don't have any regret from this particular case. So we're calling that Nash a no regret condition. All right, so that's our intro to these payoff matrices and hopefully a context that you've seen before. Now let's bring it back to sustainability and these open access resources and collective action problems and so on. And so let's flip here to the open access case. So what about open access resources, or so-called, I'll say collective, oh, not that, action problems. All right, so this type of problem is best modeled as something that game theorists refer to as an anti-collaboration game. Anti-collaboration game. I'm sorry, anti-coordination game. I don't know why collaboration was on my mind. Anti-coordination game. That's why. It's because collective and collaboration, they just roll off the tongue. And so I was biased for that. All right, so an anti-coordination game, this is a class of games, and the open access one is sort of a particular type, but this is a class of games for which the Nash optimal solution, so the best solution will be for two players to do the different actions. So the best case is for two players to do the opposite choice. And that's what makes them anti-coordination games. They almost need to be coordinated to do the opposite. And so this works well for negative externalities. In these kind of network effects, because what we're saying is that the negative externalities are going to favor participation by one player, but not both. So if one player gets involved, they get the benefit, great. But if two players get involved, that second player is going to get less benefit than they would get if they were alone, and they're going to take benefit away from the first player. So the collective action problem is then to coordinate who gets access, basically. And so, and I guess I should write that what I mean by best, this is, going to be in the case of the Nash. All right, so that's like a bunch of words. And so let's then see what we mean by that in terms of this kind of game theoretic framework here. And so what we're going to focus on is a particular type of game known as a hawk-dove game, which is equivalent to the chicken game. And so in the hawk-dove, I'll just draw a little four square here. And put subdivisions in. All right. So in this, we've got a player one. And they can choose to either use or don't use a resource. And so in the kind of traditional way, you can view this as they can choose to fight or back away. They can play a hawk strategy or a dove strategy. In the chicken, you can say is they can view to not swerve and drive straight or swerve. So the game of chicken, when two are going straight at each other and one decides to swerve and the other one might not decide to swerve. And so if you don't swerve and the other one swerves, you win. So, just because we're talking about sustainability, I'm going to put it in terms of use and don't use. But again, you can think of it as hawk, dove, or swerve and not swerve. So in the player one, I'll just say that the strategies here are use and don't use. So use the highway at rush hour or don't use the highway at rush hour. And player two, you, again, either don't use or use. And so player, if both don't use the resource, then they tie. So this outcome. So I'm just going to put, they're both going to get a reward of T. Now, if player 2 uses the resource and player 1 doesn't, then player 1 loses and player 2 wins. So player 1 will get L and player 2 will get a W. Symmetrically, if player 1 uses the resource but player 2 doesn't, then player 1 wins and player 2 loses. And so we say that player 1 gets the W and player 2 gets the L. If they both use the resource, then it's another type of tie, but it's like a really bad tie. So in that case, we're just going to call it X. So we can view that as a bad tie. And so those end up being sorted out as being that for a hawk-dove game or a chicken game, then we've got that winning has to be best, and that is going to be better than the tie, which will be better than the losing state, which will be better than the kind of bad tie state. So you can view this as win, and this is kind of a good tie, and this is lose, and this is a bad tie. And this is what is known as a hawk-dove game, or a game of chicken. All right, so that's the abstract form of it. What is, and I guess I should also then, so yeah, that's the abstract form. And I can, the Nash equilibrium for these things is either going to be, there's two Nash equilibria. And so one of them is this upper corner, and the other one is this lower corner. So I guess I can write that next to it, is there are two Nash equilibria. And that's the basically use, don't, and the don't use. And so if you landed in either of these spots, this top corner, use don't, or this bottom corner, don't use, then if the system landed in either one of these, then that will end up being kind of best for, I mean, that ends up being an outcome that at least someone is getting the benefit, even if not everyone is getting the maximal benefit out of it. And so, so those are kind of the two that you would kind of expect. But the big problem here is breaking the symmetry. So I guess I can write here that so the problem is symmetry breaking. Or in other words, who gets to win and lose. So how do you determine that? Because these two Nash are symmetric. Now, without a coordinating entity, without a third party, a culture, something like that, then you know, one solution is to flip a coin. And so depending on how big the win is relative to the lose, then how often you play your strategy is going to deter, you know, it's like whether it's a 50-50, you know, a fair coin, heads and tails come up equally, or heads comes up a little more often than tails, is going to depend on how things play off here. But one way to solve this particular problem is that every player makes their strategy based on the toss of a coin, and then on average, you end up getting things that work out okay. So that's one way to do it. And in the case of a highway, and I'll get the highway example, you can think of ramp metering as maybe one way to kind of help with that. It's a little bit not quite the best metaphor. But the other way you can do it is so-called coordinated equilibrium. And so in a coordinated equilibrium, you can have a third party that ends up telling one party what the other party has been told to do. And then your choice, so well, I'll get to an example in a second. Then your choice is, do you do what that third party is going to do? You can renege, you can decide to go against what that third party says, but is it beneficial for you to do that? So in the case of a stoplight, for example, both people want access to the intersection. A third party shows the green light. And a green light, when you see a green light, that means that the other party has got a red light. And so the other party is telling you, the light is telling you that the other party is going to stop. And so you should feel free to keep going. Now, if you're on the red light side of that, then your choice is to say, do I stop at this red light? The fact that I'm showing a red light tells me that the other party has been told to keep going. Now, I could just ignore the red light because I want access to that resource. But I am pretty much assured that the other party is going to go through regardless of what my decision is. So in that case, because I don't want to get into a crash, then I better hold off. And so having that third party there acts to correlate these equilibria. So that's what's so-called a correlated equilibrium case. And that ends up resolving this particular problem. But without having an institution of some sort to come in, then the best you can maybe do is do coin flipping. And even coin flipping, even coming up with having everybody agreeing to coin flip, that also sort of implies that there's some institution there that's allowing people to do that. So it's a big problem to figure out who's the winner and who's the loser in these particular problems. All right, so what does one of those problems look like? So the more concrete example is I'll say, well, what if, for example, player 2, so I'll draw my little grid here again. And that grid is going to be, well, I didn't really plan this out, so we'll put it here and move that over a little bit. And so in the highway case, we can imagine that this is, say, player 2 makes the choice of either side streets or highway. And I'll draw my dividers. And then we have to make the decision for player 1. And we say that player 1 they also could decide on side streets and or highway. And then what are the payoffs here? Well, I'm not going to give particular numbers, but we could give numbers in terms of what time they get home, for example, or whether they got home ahead of each other. And so I can say that, let's just say that if they both take the side streets, then they both get home at normal time. So that's kind of like them both, having an equal payoff. Now, if they both take the highway, then in that case, they both get home very late. And then I can say, well, what if there's a mixed, what if player 1 takes the highway and player 2 takes the side streets? Well, in that case, player 1, or I guess I should say, player 2 beats
player 1 home.
So in that case, you can say that,
And this is maybe faster than usual too. So I'll say faster.
So you could say player 2 wins in that case.
And then in the flip side of that, player 1 beats player 2 home. And again, basically player 1 is faster than normal.
And so
This is just a demonstration that highways at rush hour are example hawk-dove games and that comes from them using an open access resource.
And so we know that the big problem with open access resources is the non-excludability. So what are some different ways that we can solve this? Well, we can make it, we can use, say, tolls, for example. So basically we can do things that from the supply and demand analysis side, internalize an externality. From the game theoretic side, they end up solving the coordination problem. So they end up solving this symmetry breaking problem. So by having a gatekeeper controlling access to the highway, then you end up providing a way in which you can ensure that some individuals will benefit and other individuals will have to go a different way. So by putting up by raising the price enough, you're going to force some individuals to take the side streets and the other individuals to go onto the highway so that there isn't the same symmetry that causes the problem. All right, so that's the game that, that we use to talk about the open access case. This, and I'll just highlight that, the hawk-dove game or the game of chicken is specifically in the case of open access resources. In these collective action problems. Now I want to do one more before I stop with you here, and that's revisiting public goods in this kind of game theoretic approach. So let's then talk about public goods. From this game theoretic perspective. And so in these public good games, these are fit within a series of games known as coordination games. And so notice that back here, in this open access case, we had anti-coordination games. And so these are kind of the opposite of that. These are coordination games. And what do we mean by coordination games? Then these are cases where the best solution or the best outcomes occur when I'll say both players here, but we can generalize this to more than two players, but both players agree. I don't want to say agree. Both players choose the same strategy. So this is the most generic form of what we mean by these coordination games. And the public good games get further specialization on top of that, where you might prefer one strategy over another due to the positive externality. But let's just keep it general for just a second. And so in these coordination games, they're going to take a form where you've got, if I put our little matrix back in here,
All right, so this is going to take the form where we've got player 2
and they can choose to do some strategy that I'm going to generically call alpha and beta. And then over in player 1, and their two choices are also alpha and beta. Maybe I'll write them upright. All right, so if they both agree, then we are going to get an outcome where player 1 receives capital A and player 2 receives lowercase a if they both agree on alpha. And if they both agree on beta, then we're going to say that player 1 receives, I'll call it capital D, and player 2 receives lowercase d. And then in between, if player 1 plays alpha, player 2 plays beta, player 1 is going to get a C, player 2 is going to get a lowercase c, and then not surprisingly, we'll just call this B and lowercase b for this other case. And what makes this a coordination game is that lowercase a, we'll put that in the other color, lowercase a is greater than lowercase c, and lowercase d is greater than lowercase b. And likewise, on this side, uppercase A is greater than uppercase C, and uppercase D is greater than uppercase B. All right, so, and I guess it might be interesting to note, maybe I'll put this in gray over here, that side note, in the anti-coordination games, you have that the uppercase B is greater than A, you've got that C is greater than D, and you've got then the flip of that, lowercase c greater than lowercase a, and greater than B greater than D. And so this here is from the kind, if you look back at the previous slides, then an anti-coordination game is where you want the players to disagree. And so the anti-coordination games, then, you know, those are these cases here. And so you can double check that these fit that other template. And so if we know that it's an anti-coordination game, it's going to have a certain Nash setup. And if it's a coordination game, it's going to have a different Nash setup. And that's why we kind of form them into these generic categories, because then we can analyze the category as opposed to each individual game every time we play it. So in this particular category of games, for these coordination games, then you're going to find that you get these Nash Equilibria, which are up here. And down here. So both of these end up being Nash Equilibria, corresponding to the outcomes where the two players choose the same strategy. So it's always better to choose the same strategy, but then the question is going to be which same strategy are we talking about here? So that is our generic form of the coordination game. And we are going to focus on a specific type of coordination game called a stag-hunt game. So I'll just maybe write that here, and then just to give us more space, I'll go to the next page. So the stag-hunt game is our public goods case. And so this is our special case for public goods. And so what is a stag-hunt game?
So a stag hunt game, this is a type of coordination game that has the particular structure where we're modeling, so we're talking about a stag hunter. Imagine two hunters, and they either can hunt for a large prey, a stag, a large game, stag, or small game, a hare. And so a player 2, their choices are they can either choose to hunt for either one of those, the stag or the hare. And then likewise, player 1 can choose the stag or the hare. All right, so you say, well, what's so special about these things? Well, a stag is so large that in order to really be successful at getting the stag, then you need both players to work together. And so in the case of a stag, you really need both to choose the stag. In the case of the hare, both can choose a hare, but either one can actually catch the hare on their own. And if they catch them together, they have to share the hare, and it's a smaller animal, so there's not as much to share. And if they catch them separately, then the chance of them catching the biggest hare is kind of reduced. And so if you're running around the forest, there's a certain amount of hares available. You can catch one, but if somebody else is also looking for the hare, then there's the kind of expected size of the hare you're going to get is going to be smaller. And so we can model this with payouts that look like this. And so we're going to say that if they both go for stag, then player 1 is going to get rewarded by A. Player 2 is also going to get A. If player 1 goes stag and player 2 goes hare, player 1 is going to get C. Player 2 is going to get B. And then on the flip of that, if player 2 goes stag and player 1 goes hare, then player 1 will get B. And player 2 will get C. And then if they both go hare, then they both get D. And these things are such that A is greater than B, is greater than or equal to C, is greater than D. So if you have a payoff matrix that is shaped like this, that has this structure, and this set of inequalities, these relationships, that is the so-called stag hunt game. And so when I said before on the previous slide that because this is a coordination game, then we would expect that we're going to get a Nash Equilibria up in this corner. And we're also going to get a Nash Equilibria down in this corner. And so even though these are both Nash Equilibria, then you have here, we have a Nash with small rewards to both. And then up here, you have a Nash with large rewards to both. And so this up here is our Pareto efficient. It's not even, I mean, I'm actually going all the way to say Pareto. I don't even have to qualify it with Kaldor-Hicks. This is Pareto efficient. And so this box here is really our socially efficient outcome. So maximizes social welfare. There's no Pareto improvements that can be made from there. That's the place we want to be, right there. But there's still going to be this temptation to go to the small one here. And so that's going to be what ends up happening in this stag hunt, is that even though both players can get involved, then there's still always going to be a temptation for one to sort of benefit from the efforts of the other and go it alone. And so, so that's, you know, instead of hearing stag and hare, you can think of stag as a cooperate and hare as a go alone, and possibly benefit from others who are cooperating. And so that brings us back to our public goods case. So this reminds us of public goods. So let's see a numerical example of a public goods game that is set up like one of these stag hunts. And so I am going to flip to another page here. And so we, public goods example as stag hunt game. So I'll set my payoff matrix up here the same way, little 3x3 block. Draw my dividers. And so in this particular case, I'm going to say that player 2 choices are to either contribute to a public good or free ride. And so we can imagine this is in the context of, say, pollution abatement. In which case you can think of choosing to contribute means you're going to put in money to reduce the amount of pollution that you're putting into the air. You are paying for pollution abatement. You're paying for abatement. Remember, abatement is a good. But that good is going to bring you benefits, but also benefits to the rest of society. And so other people are going to get those benefits too. And you'll get benefits from their abatement. So that's what I mean by contributing to this public good. You can also think of this as, say, public radio. That's an easy one, where you imagine somebody could be contributing to a public radio station, and they are, and that allows the public radio station to put programs on the air, but anyone else who can turn on the radio can also benefit from those programs. And so they can decide to free ride. So in the first case, the clean air, so pollution abatement, this is kind of clean air.
And so, you know, clean air to breathe. And then public radio, you could say this is interesting air. You know, if we want to think that in one case it's the air you breathe, the other one it's the air waves that bring radio to your ears. So both of those, clean air and interesting air, are public goods that are subject to free riding. So just how player 2 has those choices, player 1 also has those same choices. So player 1 can choose to contribute. Oh, I'll write the contribute in the corner. Or free ride. All right, so then if player 1 and player 2 both decide to contribute, then let's say they end up receiving some benefit. Now, keep in mind that by contributing, they're putting in money. They're sending money to the public radio station. They're investing in scrubbing equipment to make their smokestacks cleaner. They are putting effort in. But because everyone else is putting effort in, then the network effect creates a synergy, creates a positive externality. And that positive externality ends up making them all benefit more than they put in. And so I am going to, you know, call that 10 here. So they benefit by 10. They both get 10 out. And we're saying that that is, that's due to, I'll just say that a positive network externality effects create synergistic benefits that compensate for costs. And so we'll see how that all shakes out as we populate the rest of the table. But that's kind of the key, is that why this is going to be the socially efficient solution here. Now, it could be the case that player 1 decides to contribute, but player 2 is just going to free ride. And so in that case, player 1 is putting in, well, before I kind of handle that case, let's imagine they're both free ride. So if they both free ride, I'm going to call that 7. And so down here, this represents that there is some background benefit. You could say, well, where does this background benefit come from? Well, you know, if that's just the background air quality, you know, it's not, you know, if you live in an area where the pollution is not so bad, even with all of the producers polluting unabated, then it's just the background air quality you get. Or you know that there's some people out there, maybe not these 2 players, that are contributing to public radio, and so there is some background level of programming that the public radio station can provide you. And so that is this background benefit of 7. Now, what if, so that's if neither of them are contributing. So what if player 1 decides to contribute, to put effort in to this public good, but player 2 does not? So what we're saying here is that in this particular case, even though player 1 puts effort into it, because player 1's benefit is purely due to the effort that player 1 is putting into it, then it's possible that that benefit is not going to compensate player 1 enough for their costs. So it's possible that the return to player 1 will actually be less than the background benefit they could get if they were free riders. And so now they've actually gone down. So they've gone from the 7 down to a 5 by going from free riding to contributing. But the benefit that they have put into the public good has benefited player 2. So while they have gone down, player 2, on the other hand, has actually gone up in benefit. So for player 2, we're going to put them at an 8. And then I'll flip that in the symmetric case down here if their roles are reversed. And so we can see here that the free rider benefits from the effort put in to the contributor, and the contributor pays. And so this here is a Pareto, this corner over here is a Pareto improvement from all of the other boxes. This is the socially efficient solution here. This is where you kind of want society to be. But because of this payoff matrix, and I guess I can, just to make it clear that this is a stag hunt, I'm going to write my stag hunt conditions. A is greater than B, is greater than or equal to C, is greater than D. In this case, A here is equal to D, or is equal to 10, B is equal to 8, C is equal to 7, and D is equal to 5. And so this here is a stag hunt. And in this stag hunt, even though we would really like this to be the case here, this Nash equilibrium is always going to be a problem, because it's always easier to be a free rider, because the free rider doesn't have to, the free rider runs the risk of being left out as being the only one paying for the good. So even though everyone would benefit if they all contributed, then in the end, no one contributing ends up being the safer bet. And so this solution down here ends up often being what you're kind of stuck with. In reality, both of these are Nash. I mean, if everyone played this, then unilaterally, there would be no reason to change away from that. So this is a Nash Equilibria, and this is a Nash Equilibria as well. So I could highlight both of these. They are truly both Nashes, but you're not going to get everyone to play this one. So what ends up happening in a population is you tend to get a mix of the two Nash equilibria with a population of contributors or members and a population of free riders. So from looking at that, you might say, well, gee, it would be nice if we could cut these, these free riders off. Well, that's the whole point of public goods, is that if it is a public good, you can't cut them off. By cutting them off, like say going from public radio to satellite radio, so where you actually have subscribers, then in those cases you've shifted from a public good to a club good. So you've added property rights, you've added more ownership to it, and you've taken out that non-excludability. And so again, it's the non-excludability that really causes the problems in these open access and in these public goods. And a lot of times our solutions, whether they be coordination or taxes or tolls or whatever, in the end, basically they are chipping away at that non-excludability. So view non-excludability as a potential sustainability problem when you're considering these solutions. And you can either view it through the lens of the supply and demand curves that we're used to working with here, or you can view it in terms of these game theoretic models where you've got these Nash equilibria, and that, you can see that the Nash are probably places that people are going to land on their own. But if there's multiple Nash, you're probably going to have a mixture of solutions throughout. And if you want to sort of make sure that one is dominating over another, then you might need to say, change the nature of the good so that's, excludable, not non-excludable. All right, well, I hope that helps in seeing this as a different way to pose these analysis, the different analysis method for these types of incomplete problems here, the open access and the public goods.